we talk about the filter architecture. The next topic, how we're going to design filter. There is a lot of different filter design algorithms that exist. One of the famous one is the Butterworth filter design. What is the Butterworth filter? Here is definition. Nth of the Butterworth filter with the corner frequency of omega 0 are defined like this way. Here is a two design parameter. One is a filter order n. The other one is a corner frequency over omega 0. When you apply the filter for image or the frequency, you need to carefully select or interpret what is the corner frequency and what is the filter order. When we do the practical problem solving, we will I would like to mention that one again, but at this moment it's enough. It is just a function like this one, binomial function, 1 plus omega over omega 0 to the 2 to the n. Okay, let's plot that one with Excel. What's gonna happen? Okay, I would like to plot nth order filter response of this one. At this moment, n is given as for example 3, whatever, and omega 0. At this moment, I would like to normalize as 1, and omega are changing from here. The step, exponential step is 1 over 1.45. Okay, 1.5, and plot. This one is actually log scale if you're plotting like that. So I would like to check up that up to 100 around here. Okay, it's okay. It's 30. Okay. I would like to plot a little bit finer. Okay, that will be better. Then you will change it to here. I reduced the steps up to 50. Okay, and then I would like to okay, absolute value of h. Okay, absolute value of h is square root of this one, so I would like to square root 1 plus omega divided by omega 0. This is a constant, and taking square and the square root. Okay, this is. So this one shows that the h response, and I would like to plot that one here. Okay, this one is a third order Butterworth filter. Okay, I think I need to plot that one into dB scale. So I need to dB each. Take the dB scale. To taking log scale, I need to 20 times log 10 and this one. So I need to plot this one, not by the linear step. Okay, I have to check. Okay, this one is magnitude response and frequency up to 50. If my memory is correct, it was 50, and this one is another 50. Then okay, what is that? Okay, I think this is removed. Okay, and also I need to take this part as a log scale. It should be okay, this is log scale. Then this is the border plot for this function. In this case, its corner is normalized at 1. Okay, and filter order is 3. What if I change the filter order up to 4? Then does that change anything? 5. Okay, I think I didn't include that filter order. The 2 to the n is omitted here, so I need to multiply 2 times n. Not this one. So I need to include this part, the constant. And okay, first I would like to try with the 1, filter order 1 first. Okay, this one is a filter order 1 case. What about 2? So you can, I need to fix up this one up to, it should not be. Okay, I need to fix up that one. 3, 4, 5. What's the effect of the filter corner? You know that it's a much steeper as a filter order is increased. In the first order, it looks like this one. In case of second order, it's a little faster decreasing, and the third order is faster, and the fourth order is faster. The filter corner are given here is very smooth. You can see the filter is very flat on top of here. It's a maximally flat filter is another name of the Butterworth filter. Here shows the explain about the Butterworth filter. It's known as maximally flat magnitude filter. There's no peaking effect. It's smoothly cutting out the unwanted frequency component. Okay. So we would like to design this the Butterworth filter. We studied what is the response of the Butterworth filter. So we would like to design this kind of transfer functions. So in case of first order, it means n equals to 1 case. In that case, HS has this kind of form. We can take plus sign or minus sign, doesn't matter. But if we taking the plus, it is the stable response, because a pole located in the left hand side. The 1 over omega 0 expressed as a tau. Okay, so HS can be expressed in these two forms. These two forms, S plus 1 minus omega 0 over omega 0, has this first order Butterworth filter response. If you replace J omega, then you can prove that this one is a typical response of the Butterworth. First order means that there is a single pole exist. In that case, we need to take a stable system response. Pole should be located on the left hand side, so it is S plus 1 over it should be omega 0 and omega 0, this kind of forms. If you multiply omega 0, then you can see here that the minus sign, case S is positive omega 0, that is the right hand side, so we need to take the left hand side pole, so S should be this one. So in that case, HS are given like that. That case is pole located in this point. Okay, this one is first order filter. What about second order filter? In the second order filter, to have you know that n is 2, then omega over omega 0 over 4. Okay, omega 0 over 4. To have this kind of magnitude response, transfer function should be like that. So S over omega 0 should satisfy these conditions. Plus minus J can be expressed in the general angle. It looks like this one. So S should be omega 0 times exponential J 2n plus 1 over 4 times pi. So to have a stable response, all poles should be located left hand side. So we can choose n equal 1 and 2. Then it will give two different poles here and here. Okay, the angle is 45. The magnitude is omega 0, so this magnitude is omega 0, but what is the angle difference? We can choose n equal 1, then that's the 3 pi over 4, that's this point, and n equal 2 is 5 pi over 4, that's this part. So the magnitude is omega 0, angle has two different values like that. Each one is, if you measure from here, it's a 45. This angle is right angle, 90 degree. So this is second order filter. So we can think one more thing, and the third order filter. This one is odd one. In that case, HS given in this way. So you can, using the generalized solution, and select the stable poles. Stable pole means left hand side solutions. That's the magnitude is this one. Angle is separate like this way. 0 is this point, and the plus 1 is at this point. Minus 1 at this point. So this one has these 3 poles. So if we're selecting equal angle like this one, the 3 different poles are selected left hand side with the corner frequency is the radius of the circle. So pole can be defined, selected by this way. the angle is important compared to second order. Second order cases there is no real poles, complex two different poles. In the third order poles, one real pole and two complex conjugate poles. But first cases, first order, it has one real poles. First order, third order commonly has a real poles. Okay, we can generalize this one in case of n is odd or n is even. N is odd means the first order or third order is odd case. In that case, is the value is a plus minus 1. That's this one. But in case of even, by taking the square, this becomes a real number. So the constant part should be complex number. That's why it is plus minus j. Okay. So even cases we have to follow these rules. In case of odd, we need to follow that way. So odd cases, the real part is 1 because this becomes the complex. And the even cases, this becomes the real number, that this should be complex number. So that is the basic rules. So we would like to design nth order by assuming that n is odd. Then we can select the pole location by use of these equations. N can be choosing from here. Then we can select n different poles in the left hand side. This is the odd poles. We can selecting poles with the angle difference is pi over n, and number of pole is n. Okay, the radius of this circle is corner frequency omega 0, and even cases is the same. The angle difference is pi over n, and we can select left-hand side poles with the equal angles. And in case of even, there is no real poles that exist, but in case of odd, it has a real pole, and all the other is complex conjugate one. So this is how to design the Butterworth filter in case of n is odd or n is even. Okay, here is an example. We would like to design a Butterworth filter with corner frequency is 10 kHz and stop band frequency is 50K. We didn't mention what does that mean of these stop functions. It means that when we testing the frequency response, magnitude are decreasing in certain corner. This frequency is called corner frequency. This is F0 frequency. Stop means that we need to provide the suppression levels. Suppression level means that we have 60 dB suppressed. At this point, frequency is Fs. That's the stop frequency. So this one is a corner frequency, but this one means the stop frequency. Stop frequency is specified for the selecting the order of the filter. We need to design n, and corner frequency is given, but we need to select n. Proper n should be chosen. At this moment, the DC gain is 0, means this one is 0 dB. As we have done, most of the example we talk about is 0 dB DC gain. It means when I plot this one, you know that this one is 0 dB. This means DC gain is 1. 1 means 0 dB. Okay. You know what? Log 10, 1 is always 0. Okay, so 1 means 0 dB. If you multiply 20, it doesn't matter, because by definition, log 1 is 0. In any case, that's just 0 dB DC gain. So we need to design that satisfy these conditions. And the first one, we need to select the proper filter order, and we know that the filter response of this one. Filter response are given like that. So omega s is given here. 2 pi times fs is omega s, and corner frequency omega 0 is also given. And we didn't know the n. And we take the dB scale at here. So actually we have to take a 20 log 10, but you know that h given as a square root 1 plus omega s over omega 0 to the 2n over 1. So 20 log, you have to take in 20 log this one, but square root will removed and that becomes the 1. That's this one. So I removed the square root over here. That's why 20 log converted to 10 log. Okay, anyway, this 10 log means the suppression level at omega s. This suppression level is this one, should be less than 60 dB, these conditions. So this condition are given here. The suppression level should be more than 60 dB. So this one is more than 60 dB. So that's these conditions. From this relationship, we need to find the proper n. N should be integer number. This can be converted into these equations, and fs and f0 are given 10k and 50k. So we know that these values. Then if you calculate n is a 4.29. So n should be larger than this one. So you need to select n as a 5. So the first step, we need to choose proper n by use of this suppression level at the fs is 50k. The next step, we need to select the proper pole. At this moment, n is odd. Okay, so we need to follow these odd case rules. Then we can choose the pole location like this one, and n is given in such a way, and the s will be minus omega 0. You can see that's this part. Minus omega 0 is this one, and minus omega 0 times e to the plus minus j pi over 4. There is 2 poles are selected here and here. This angle becomes pi over 5. Order is 5. And the another one is here and here. And this angle is also pi over 5. That's this one. Then we can this pole implemented here. And these two poles, by summing, by adding the two different complex conjugate pole, so sum of root are given this way, and product of the root are given omega 0 scale. This is the second order system. That's the curve given by these two poles, conjugate two poles give the second order system. And the last one is this one is 2 pi over 5. That's this two part. Two complex conjugate root are added, then it will give this coefficient, and by producting will give this one. So the sum of two root or product of the root will give this second order system. So we defined transfer function of that one, and from here you can find out the impulse response and stem response of that one. From here you can see a second order system expression. You know that there is a two complex pole will give a second order system like that. It's similar to here, except this one is a first order. So when we implement a filter, we usually take in the second order lattice structure that is expressed here. In the second order lattice structure, the all coefficients are real number, even though there is a two complex number complex poles exist, but it's a conjugately related. So by sum of two root is real number, and product of two root give constant terms. So we can naturally using this lattice structure to implement the second order system. How we going to implement that one? That is shown over here. I would like to show you. This one is Python code, but you can do the same thing by use of a MATLAB. At this moment, I would like to use the Octave. Okay, here you can use the MATLAB. In case of MATLAB, you don't need to loading some kind of package. But if you are using Octave, you need to check up you have a signal package here, and you need to load that one. EKG load signal. Then you can using the function. So I would like to show you how to implement these functions. Okay, make it clean. And I would like to make these functions from here. Okay. So first, I would like to define h1 function that will implement this first order one. So that is a transfer function. The first of coefficient is 1 and omega 0. Okay, I need to define f0 is a 10k. Okay, and omega 0 is a 2 pi times 10k. Okay, this is omega 0. So h1 can be defined by transfer function. The numerator coefficient is 1 and omega 0. and denominator is 1 and omega 0. Okay, I write down this one. So h1 expressed in, okay, I need to make it 0. Okay, here is s should be 0. Okay, this is it, 0. Okay, so numerator 0 omega 0 means numerator is only omega 0, denominator is s plus omega 0 can be expressed in this way. So this one is the single or first order transfer function of the first one. The second one can be defined similarly, transfer function, and the numerator in this case is 0, 0 and omega 0 square. Okay, this is numerator. Okay, at this moment only omega 0 square exists here. The denominator is 1 and 2 times omega 0 times cosine pi over 5. This is the coefficient of s. The last one is omega 0 square. Okay, this is second order filter for H2. Okay, this is the second order filter H2. And the last one is in the same way, transfer function of numerator is 0, 0 and omega 0 square, and denominator is 1, 2 times the omega 0 times cosine. At this moment is 2 times pi over 5. Okay, and the last one is omega 0 square. Okay, I defined the 3 different transfer functions, but the HS is a product of all these things. So I need to h1 times h2 times h3. Then this is this function. This one is expanded one, but this one is factored as a second order system, but it's the same things. So first I'd like to check the impulse and stem response, and then I'd like to testing the frequency response of that one. So first, how we're going to testing the impulse response? To do that, I need to define the time series variable. Time will be changing linear space from 0 to the about 20 times omega 0, and the 101 number of point is this one. And I would like to test the impulse response of this one. Impulse response of HS. So HS is this one, and the time is provided here. Okay, I calculate the impulse response at here, and I can plot the one TS times HS. Then I get the impulse response of that one given like this way. If the impulse is provided at t equals 0, then response will be given in such a way. So as time goes on, the impulse effect is the decay out. And what about the stem response? By S is a step response of HS and TS, and plot TS and YS will give, sorry, it should be small capital. And that gives the stem response. I give this stem response. It's overshooting and fluctuating and converging to the unit step. This is stem response of this Butterworth filter. Lastly, I would like to testing the Bode plot. Make a Bode plot by use of this transfer function. To create Bode plot, you need to specify frequency range. To specify the one frequency range can defined like log space. The starting frequency is 10 to 2. This one is 100 Hertz, and we'll finish at about 7. 7 means maybe 6. 6 is 1 megahertz. So at this moment, the corner frequency is I need to starting from the frequency series. Okay. Frequencies are starting log space, starting from 100 Hertz and 1 megahertz. And the number of points is 101, and the frequency, the angular frequency series can be found by 2 pi frequency. Okay, so to get the Bode plot, I can using that help Bode will give the how you're gonna use that one. So here is the pattern, magnitude, phase, and the angular frequency are returned if you give a system function and frequency list. So magnitude HS, and I can do that. Magnitude HS and phase HS and omega angular frequency are returned by Bode function, and I provide the system function, and the frequency series are provided here. Then I can plot, make a border plot by use of a log scale and along the frequency axis. So I have the semi-log x. So x-axis plotted over log scale, and I provide the frequency, and magnitudes are plotted in dB scale. So I take the log 10 and magnitude response. Okay, this one will give the border plot. So you can see this one is the border plot. I need to range is too large, so I need to specify the axis 100 to 1 megahertz. This one is x-axis range. Y will be minimum is 100 and maximum is 0. So I would like to plot that one in this range. Then I can find out the 60 dB is around here. We know that this is a 10 kilohertz. This is the corner frequency, and at the stop frequency it should be 60 dB. So this is a 20K, 30, 40, 50. So if you follow the 50, that will be around 60 dB. So that is the requirement in our the filter. Border plot are implemented here. You can prove that by the same way. Here shows that the pole selection, we have 5 different poles. 1, 2, 3, 4, 5. 5 poles are selected here, and filter response are plotted at here. The magnitude response shows here that we designed the corner is 10 kilohertz and 60 dB suppression after 50K. So that is this part. So corner frequency is a 10 to the 4. So this is 10K, and our design requirement is 50 dB suppression at the 50K. Okay, this one is around 50K. So 10K, 50K, this is 100K. So this is meet our requirement. The right hand side is stem response are plotted over. This is peak, and overshoot level is this one. Peak time are given here. So by use of these two things, you can characterize the stem response. And from here, we studied how to design the filter and how to implement that one, and how to confirm the functional behavior. And the lastly, we talk about pivot stability. And pivot stability means a bounded input cases, bounded output will come out. So this one related to stability. Bounded input, bounded output stability means that if input is a bounded input is applied to the system, then system output will be bounded. So finite input will give a finite output. To satisfy the condition, HT should be absolutely integrable. That's these conditions. If this condition satisfied, the system guarantees the existence of Fourier transform. To exist this Fourier transform, the impulse response should be absolutely integrable. The another point of view, in the Laplace transform, the j omega axis, when we draw the S domain, in S domain, the y axis is j omega. Okay, this one is a real value. So reasonable convergence including this j omega, then Fourier transform exists. That is another expression for the pivot system. If a system is causal and stable, then all pole HS must be in the left-hand side of the S-plane. It means these conditions. So in the S domain, pole should be located in the left-hand side of the S-plane. So this one means that as time is causal, means that T goes to the positive, it's a right side signal, and to be stable, something like this one. So in this case, it's pole located -1. Okay. If a pole located at +1, then it means e to the t. So it is not that stable. As time goes on, then this diverging, but this one will converge. So in this section, so what's the meaning of bounded input, bounded output stability? And the requirement is absolutely integrable of impulse response. That's the pivot stability. Another expression for that condition can be expressed by the reasonable convergence of that. And also, if system is causal and stable, then HS must have all ports should be left on the side. So that's all.